In this lesson, we want to talk about solving trigonometric equations by factoring. All right, so now we're just going to look at the next scenario. We already talked about how to solve these basic trigonometric equations using linear methods. Now we're just going to be factoring. So we have 3 times cosine theta plus 2 times cosine squared theta equals -1. So a very easy problem. You want to get this. If you see something with a squared term in it, you want to think about factoring right away. Okay, that's usually how you're going to solve that. And you want to think about getting it in the form of ax squared plus bx plus c equals 0. Okay, remember this is a quadratic, and you're able to solve this by factoring and then setting each factor equal to 0, right? That's the 0 factor property. So I'm going to do the same thing here. I'm going to move this to the left, basically. So I'm going to say I have 2 times cosine squared theta, and then plus this 3 times cosine of theta. And I can add 1 to both sides of the equation. So say plus 1 and this equals 0. So if I can factor the left side, again, I can use that 0 factor property. There is a tremendous roadblock to factoring this when you first start. I don't know why it is, but when I work with students, and I'm just going to do it on the first one, I tell them just make a little substitution. So in this case, you're working with cosine of theta. So just let something like u be equal to the cosine of theta. Okay, so everywhere you see cosine of theta, replace it with u. So here I have cosine squared theta, which is basically cosine of theta squared. So I would say I have 2u squared plus, in this case, 3u, and then plus 1 equals 0. So from here, could I factor this and solve it using factoring? Yes, of course I could. So this guy is a prime number, and this guy is 1. So this is really easy to factor. This is going to be 2u, and this is going to be u. We know that off the top. And we know that because this is positive 1 and all the signs are positive, the only possibility is that this would be 1 and this would be 1. So basically you would check this and say, okay, well 2u times u is 2u squared. The outer would be 2u, the inner would be u. So those combined together would give me the 3u, and the last would be 1 times 1, which is 1. So we're good to go. So you could have factored this the same way using the same principles with the cosine of theta in there. But again, I use u there just to avoid the little roadblock of first factoring a trigonometric expression like this. So what I want to do now is, because u is cosine of theta, I just want to plug back in. So I'm going to say 2 times, everywhere there's a u, I'm plugging in a cosine of theta, then plus 1, and then times, you have your cosine of theta, plus 1, and this equals 0. So now that we've got this guy factored, let's set each factor equal to 0, and let's see if we can get a solution. So I'm going to start with this one. I'm going to say 2 times cosine of theta plus 1 equals 0. Let's subtract 1 away from each side of the equation. We're going to get 2 times cosine of theta is equal to -1. Divide both sides by 2, and I'm going to get that the cosine of theta is equal to -1/2. So you're going to see the same numbers pop up over and over again. You probably at this point know that the values for this in terms of degrees would be 120 degrees and 240 degrees. But I'll go to the unit circle in a moment and show you. So let me just erase this, kind of make this a little bit more neat. And I'll just say that cosine of theta is equal to -1/2. Let me just slide this over just a little bit. And I'll delete this from here. And I'm going to go down to the unit circle all at once. So let's do this side now. So we have cosine of theta. Basically, you're just subtracting 1 away from each side. So let's do the full thing. So plus 1 equals 0. Subtract 1 away from each side. You get cosine of theta is equal to -1. You probably know already this happens at 180 degrees, or pi if you're thinking about radians. So let's move this up and say we have cosine of theta is equal to -1. So let's go to the unit circle real quick and get all of our solutions. Again, you can also do this using your calculator. You can do it with special triangles. There's so many ways to do it. But for the first two, they're very easy. I'm going to give you a final problem where you have to use your calculator. There's no other choice. Okay, so we'll see that. So let's go down to the unit circle. So again, if we're looking for cosine of theta is equal to -1/2, and then cosine of theta is equal to -1, where you're looking for an x value of -1/2. So that's going to happen here, again, at 120 degrees, or 2 pi over 3 radians. And then also, remember, this guy would have a reference angle of 60 degrees. So you would want 240 degrees because that also has a reference angle of 60 degrees. So this is your -1/2 there. Again, 240 degrees, or 4 pi over 3 radians. So let's write 120 degrees, and then I'm going to write 240 degrees out here. I'll put a little space here because I'm going to put this 180 degrees here for the -1, right? So -1 is your x value there. So let's put 180 degrees there. And let's just put the radians in there as well. Generally, you're going to give your answer based on the restriction you get, right? If they tell you the interval is between 0 and 360 degrees, you put degrees. If they tell you 0 to 2 pi, you put your radians. So let's go ahead and put, we have 2 pi over 3. we have pi, and then we have 4 pi over 3. So let's go ahead and copy this. We're going to need that, and we're back here. So let me just go ahead and paste this in, bring this over here. So this is going to be our solution. Again, if you restrict the domain, so for this one, let's say that we restrict the domain from 0 degrees to 360 degrees. Okay, so basically in that interval, for this one, this is going to be if you restrict it from 0 to 2 pi, okay, in terms of radians. So based on what you get, that's how you're going to get your answer. If you're asked to get a general solution, remember, these guys are going to repeat, right? So with the sine or cosine, if you're working with one of those, the period, okay, is going to be 360 degrees or 2 pi in terms of radians. So just take this. If you wanted a general solution, so let's put general solution here. You would take these guys, so I'm going to say 120 degrees plus 360 degrees times n, where n is just any integer. You're just going to take all of them. So then 180 degrees plus 360 degrees times n. And then lastly, 240 degrees plus 360 degrees times n. Okay, let me close the set braces. Then for this one, remember 360 degrees is like 2 pi in terms of radians. So what I want to do here is say 2 pi over 3, and then plus, we'll have 2 pi times n. Okay, so n is any integer. Same thing, so pi plus 2 pi n, and then lastly 4 pi over 3 plus 2 pi n. So we have our general solution here, and then we have our solution where basically we're in an interval. You could say you're restricting the domain. All right, for the next one, let's look at 4 equals sine of beta plus 2 times sine squared beta plus 3. Again, if you have something squared and then something to the first power, I'm always thinking factoring, right? I'm always thinking ax squared plus bx plus c equals 0. So I'm going to write it like that. I'm going to first, let's go ahead and flip the sides. I want everything to be on the left side that I'm working with. So let's go ahead and say we have 2 times sine squared beta plus, let's say, sine of beta. I'm going to subtract 4 away from each side of the equation. So this would end up being basically -1 over here, because if I subtract 4 away from each side, this would be -1, and this equals 0. So now what I have here, I should be able to factor. So again, if you're struggling with this, if you just can't get past the mental roadblock, go ahead and take sine of beta and set that equal to a variable like u. But I think we can get past it, right? So I'm just going to put sine of beta here and sine of beta here to start. Now this 2 in front, that's a prime number, so I've got to stick that in one of these, so I'm just going to stick it here. So we have 2 times sine of beta times sine of beta, which will give me 2 times sine squared beta. Okay, so that works. Now we have alternating signs here. Let's think about this. We have a -1 as a final term, so it has to be 1 times 1, but we have to think about the signs there. Is it going to be plus here and minus here, or vice versa? Well, the outer here would be 2 times sine of beta, but it would be negative. And then the inner would be plus the sine of beta. So that's not going to work because the middle term's positive, okay? So that means I need a plus here and a minus here. So let's erase this. And now you see it works out, right? Because the outer would be 2 times sine of beta. And then the inner would be minus sine of beta. And so if I do the subtraction, I get my plus sine of beta, and then -1 times +1 is -1. So we have correctly factored this guy. Same thing. So 2 times sine of beta -1, setting that equal to 0. Let's go ahead and solve it. Add 1 to each side of the equation. You get 2 times sine of beta is equal to 1. And I'm going to divide each part by 2 here. And basically I get that the sine of beta is equal to 1/2. So let's erase this. And you see these values so often, it's almost like you start dreaming about them. We know that this is going to be 30 degrees or 150 degrees. Again, if we're in that interval from 0 to 360 degrees, where you could say pi over 6 or 5 pi over 6 in terms of radians. So let me write this over here. So sine of beta equals 1/2. So right now I know beta is equal to, well, let me just do this in solution set notation. We know we have 30 degrees and we have 150 degrees. Okay, so far that's what we got. Let me put this in terms of radians also. So let's go pi over 6 and then 5 pi over 6. So what's going to be the result from over here? Let me draw a little line. We have the sine of beta plus 1 equals 0. Again, we're just going to subtract 1 away from each side. So the sine of beta is equal to -1. And again, if you know your unit circle, this is basically going to give us 270 degrees or 3 pi over 2. So let's get rid of this. And let's put 270 degrees. And then over here, let's put 3 pi over 2. Let me just erase this real quick. And let me just drag this out of the way. So we'll put this over here. So let's put or. And then let's come down here. And again, the more you reference the unit circle, the more you work with it, the more you memorize it. Again, we were looking for sine of beta to be equal to 1/2. So that's going to be here. You're looking for your y value. So 30 degrees or pi over 6. And then if I go in quadrant 2 where sine is positive, again, what angle is going to have a reference angle of 30 degrees? 150 degrees. So it's going to be here. Okay, it's 150 degrees or 5 pi over 6. Then if you're looking for a y value of -1, it's going to be at 270 degrees or here, or again, 3 pi over 2 in terms of radians. Okay, so let's talk about the general solution. This might not be obvious, but when you look at these, sometimes they're going to have this pattern. I know when we work with sine or cosine, they repeat every 360 degrees. But if you notice this one, if you started, let's say you went through and you say, okay, well, 30 degrees plus 360 degrees is 390 degrees. Then 150 degrees plus 360 degrees is 510 degrees. And then 270 degrees plus 360 degrees is 630 degrees. So I want you to notice that everything that I have here is just differing by 120 degrees. So if I start here and go here, I added 120 degrees, I added 120 degrees, I added 120 degrees, so on and so forth. For a general solution, in this particular case, I can say 30 degrees, okay, plus I know the period of sine is 360 degrees, but because of this, I can say 120 degrees times n. So 30 degrees plus 120 degrees times n, this would be a simpler way to write this. Then for this guy, if you want to put this in terms of radians, let's go ahead and just say that you have pi over 6. Plus, you're going to do 120 degrees in terms of radians, so that's 2 pi over 3. So 2 pi over 3. And then times n. Okay, so let's close that up. So this would be our general solution. And then this is if we had a domain restriction. So let's say from 0 to 360 degrees. And then here, let's do from 0 to 2 pi. All right, let's look at one that's much more challenging. So here, we're not going to be able to use our fancy unit circle. I think we can on one part, but on the other we can't. So we have tangent squared beta plus tangent of beta minus 2 equals 0. So same deal, I'm going to be able to factor this. And I'm just going to set this up. It's already in line for me the way I want it. So I'm just going to put the tangent of beta and the tangent of beta. So I basically need a positive 1 and a negative 2. So how am I going to get that? Well, basically I want to do positive 2 and negative 1. So this guy is factored. Pretty easy to do that. Let's go ahead and start with the easier one. So let me start with the tangent of beta minus 1 equals 0. So we'll say the tangent of beta, if I add 1 each side, would be equal to 1. So where's the tangent of beta equal to 1? You might remember from your special triangles that one solution here would be 45 degrees. Remember, tangent is positive in quadrants 1 and 3. Remember all students take calculus. So it's positive in quadrants 1 and 3. Okay, so I need to find the quadrant 3 solution. So I want the angle in quadrant 3 with a 45 degree reference angle. So I can go ahead and do 180 degrees plus 45 degrees, which is going to give me 225 degrees. So let me put 225 degrees to finish that up, and then I can erase it. So let's put beta is equal to 45 degrees or 225 degrees. In terms of radians, you could write it like this. You could put pi over 4, and then you could do 5 pi over 4. So that takes care of this part. Now over here, this is where we're going to struggle a little bit. So we have the tangent of beta plus 2. We're going to set that equal to 0. So let's go down here, get a lot of room. We'll come back up. So the tangent of beta plus 2 is equal to 0. Let me subtract 2 away from each side of the equation. I get the tangent of beta is equal to negative 2. So there's nothing you can pull from special triangles or the unit circle where you're going to figure this out. Okay, so what I would do here is go through and basically use your inverse tangent function on your calculator. Okay, go ahead and use this guy. Okay, and I'm going to use positive 2, not negative 2. If you punch this up, you're going to get 63 point, and I'm going to round this, let's say 4, 3. So this is in terms of degrees. So now what this is telling me is that the reference angle with wherever I need to go is going to be 63.43 degrees. Now tangent of beta here is negative. Where is tangent negative? It's negative in quadrants 2 and 4. So I'm looking for a solution in quadrants 2 and in quadrants 4. And what I want is the angle with a reference angle of 63.43 degrees. So in quadrant 2, I would do 180 degrees, minus 63.43 degrees, which I'll say is 116.57. So let's go ahead and write this as 116.57 degrees. And then in quadrant 4, I would do 360 degrees minus this 63.43 degrees. And that would give me 296. Let me write this down. So 296.57 degrees. So let's erase all of this. We don't need it anymore. And let's just bring this up here. And I'm going to combine all of this for one solution. So let me get this over here. And let me come up here. And I'm basically going to say, and let me kind of drag this over here. So I'm going to do one for degrees and one for radians. So beta could be 45 degrees, 225 degrees. You could have 116.57 degrees. And this is an approximation. So maybe you want to notate that this is approximately here. And then this is an approximation also. So 296.57 degrees. And then in terms of radians, if you wanted to convert this over, again, for each of these, you would multiply by, you have degrees here. So you want degrees down here. And then you want pi up here. So you would basically say that the degrees are going to cancel. So let me just show that real quick. 116.57 divided by 180. And then I'm just going to multiply it by pi. And I'm just going to round this off and say it's about 2.034. So let me slide this down. And I'll just say it's about 2.034. So let's get rid of this one. And let's do this one. So let's move this up. And basically we're going to multiply it by, again, you want pi over 180 degrees. We know that the degrees here are going to cancel. And basically I'm doing the same thing on my calculator. 296.57 divided by 180, then times pi. So let's just go ahead and say this is going to be 5.176. So 5.176. And again, you just want to show some way like, hey, this is an approximation. So I'll just put approximately like this, just showing that this is not an exact value. Now remember, if you're working with tangent, the period is 180 degrees or it's pi radians, okay? So this would be for, in the case of from 0 to 360 in terms of degrees, and I made that terribly, okay? So 360 degrees. And then this would be basically from 0, let me put my degree symbol there, 0 to 2 pi. And then for the general solution, I'm going to take 45 degrees. So let's go ahead and say 45 degrees. Plus, I'm going to do 180 degrees times n. And then I have another guy here, so I'm going to do 116.57 degrees plus 180 degrees times n. So again, this is an approximation. This is an approximation. It is not an exact value. Depending on your teacher, you might have to show that in some way. So that's why I put this here and this here and this here and this here. That's just my way of notating. This isn't standard. This is my way of notating that, hey, this is an approximation. It's not an exact value. So then down here, for this guy, I would start with pi over 4 and then plus the pi times n. And then for this one, I would take my 2.034 and then plus my pi n, okay, like this. Now again, if you want to just notate that this is an approximation and this is an approximation, just to let your teacher fully know that you're aware that this is an approximation and not an exact value. All right, let's take a look at one more problem. So somewhere in your textbook, they're going to tell you that you don't want to divide both sides of an equation by a trigonometric function, such as the cosine of beta. So when you do this, you could potentially remove some of your solutions. These are going to be solutions that make the divisor 0. So what I'm going to do is solve this in two different ways, and I'll show you how this can cause problems. So the first way is the correct way, and that's with factoring. So if you have the cosine of beta times the cotangent of beta, and this equals the cosine of beta, you could subtract the cosine of beta away from each side of the equation. So over here, this would cancel, and you'll have 0. So on the left, you would have the cosine of beta, then times the cotangent of beta, and then minus this cosine of beta. And what I'm going to do, because we're going to factor this out, let me put times 1 so nobody gets lost. And I'm going to set this equal to 0. Let me actually get rid of this because we're going to come back up and use that in a moment. So let me slide down here just a little bit. And I'm just going to factor out the cosine of beta. So this right here is going to get pulled out in front of some parentheses. So you have the cosine of beta times the quantity. Inside, you would have the cotangent of beta. And then minus, if you pull this out, you would have your 1, and then close that down, and this equals 0. So we're now going to solve this using the zero product property, or you can call it the zero factor property. So for that, I'm going to take the cosine of beta and set that equal to 0. then I'll say or. I'm going to take this other factor, so the cotangent of beta minus 1, and set that equal to 0. Well, for this one, you could add 1 to both sides, so the cotangent of beta would be equal to 1, and we know that the tangent of beta is equal to 1 over the cotangent of beta, so the tangent of beta here would be 1 over 1, which is 1. So let me write this as the tangent of beta equals 1. So the first one is the cosine of beta equals 0. So I'm looking on the unit circle for an x-coordinate of 0. So that's going to occur right there at pi over 2, or 90 degrees, and then right there at 3 pi over 2, or 270 degrees. Now for the tangent of beta equals 1, we've seen this several times already. We know that in the first quadrant, this is going to be pi over 4. Again, if you skip the other problems, you could just do the inverse tangent function with 1 as the argument. You'll get pi over 4, or 45 degrees. You could also think about this with the definition of tangent. So you could say that the tangent of beta is equal to the sine of beta over the cosine of beta. And in this case, if you replace beta with that angle, which is pi over 4, you can go to the unit circle and actually see why we're getting a value of 1, and that's because we have the same non-zero number divided by itself. The sine value is square root of 2 over 2. The cosine value is square root of 2 over 2. So square root of 2 over 2 divided by square root of 2 over 2 will give you 1. And then the period for tangent is pi. So if I add pi radians, or 180 degrees, that's going to give me my solution that's in quadrant 3. So that's going to be at 5 pi over 4, and the tangent of 5 pi over 4, again, you would have the same non-zero number divided by itself, and so you would get 1. So let me get rid of this, and let me highlight this over here as 5 pi over 4, or 225 degrees, and I'll get rid of this, and this, and this. So if you wanted to write out your solution, you could say that beta is equal to, let's start with pi over 4, and then let's go to pi over 2, and then let's go to 5 pi over 4, and then let's go to 3 pi over 2. If you want to work with degrees, we could say that this is 45 degrees, this is 90 degrees, this is 225 degrees, and then lastly 270 degrees. Okay, let me grab this real quick, and let me come back up here and paste this in here. And I'm just going to show you real quick that these solutions all work, just so that when we get to the next part, you're not lost in terms of whether we did it correctly or not. So the first solution was pi over 4. So let's plug that in there, and there, and there. And let me make that a little bit better there. Let me slide this out of the way so we can fit this. We know that the cotangent of pi over 4 is 1, and the cosine of pi over 4 is square root of 2 over 2. So this would be the square root of 2 over 2 times 1 is equal to the square root of 2 over 2. So that is a valid solution. Now, similarly, if you do 5 pi over 4, the only thing that's going to change is the cosine of 5 pi over 4, that's going to be a negative square root of 2 over 2. So if I did 5 pi over 4, 5 pi over 4, and 5 pi over 4, this would be negative square root of 2 over 2 times 1 equals negative square root of 2 over 2. So that one's going to work as well, because you get the negative of the square root of 2 over 2 equals the negative of the square root of 2 over 2. Now, the other ones are going to make the cosine of beta equal to 0. So whether you did pi over 2 or 3 pi over 2, when you plug that in, let me just do pi over 2, you're going to get 0 equals 0. And let me make that a little bit better there. So cosine of pi over 2 is 0. Cotangent of pi over 2 is actually also 0. So you would get 0 is equal to, over here, cosine of pi over 2 is 0. So this one would work, and so would this one. It's the same thing. So you can see these solutions work in our interval. So from 0 and including 0 going out to 2 pi is excluded. And then for this one, you would have from 0 degrees where that's included, going out to 360 degrees where that's excluded. Okay, let me get rid of this. And let me show you what can happen if you solve this in a different way. So let's say instead of factoring, I decided I was going to divide both sides of the equation by the cosine of beta. So let's divide this side by cosine of beta, and let's divide this side by cosine of beta. And you're going to see a problem happen. So this would cancel with this, and you'd have the cotangent of beta is equal to, well, this would cancel with this, and I have a 1. So it equals 1. Okay, well, we know this turns into the tangent of beta equals 1, and we know we get this solution right here of pi over 4, and we get this solution right here, which is 5 pi over 4. But what happened to these solutions right here of pi over 2 and 3 pi over 2? Well, those are the solutions that make this divisor 0. Cosine of pi over 2 is 0. cosine of 3 pi over 2 is 0. So that's what's going on. You're going to potentially remove solutions if you use this strategy. So what we want to do is stick to factoring when we try to solve this type of problem, because you're not going to run into these types of issues. So I just want to note real quick for those of you that are interested, you can look at this problem on Desmos. What you would want to do is go back to the fact that you have the cosine of beta. I'm just going to call it the cosine of x times the cotangent of x is equal to the cosine of x. Now, what you're going to end up doing is graphing this guy on the left and this guy on the right separately. So the graph in red is y equals the cosine of x times the cotangent of x, and the graph in green is y equals the cosine of x. So if you want to solve it this way, you're looking for the points of intersection between those two graphs. So you're basically asking the question, for which x values are the y values going to be the same? Those are going to satisfy the equation. So the ones we found pi over 4, we found pi over 2, we found 5 pi over 4, and then we found 3 pi over 2. So you can continue with that if you want. This is something you can look at on Desmos on your own if you want a visual representation of what's going on.